Hi everyone, and welcome to this session, the JVM in JDK 10. I'm Eric, and before we begin, I would like to show you all this safe harbor statement slide. Please take your time and read it through carefully. Alright, with that out of the way, let's have a look at today's agenda. First off, we're going to look at the JDK and the JVM and how they relate to each other. Then we're going to do a deep dive and look at the three major components of the JVM. We're going to take a look at the garbage collector, the runtime, and the compiler. And then last but not least, we're going to take a little sneak peek into the future and see what's next. But before we begin, who am I talking to today? I'm Eric, and I work at Oracle as a developer in the Java Virtual Machine garbage collection team. I have worked with the JVM for more than 5 years now, and I have primarily worked on the G1 garbage collector, the Metaspace implementation, and the GC/JFR events. If you want to get in touch, you can find me in the OpenJDK channel on irc.ofc.net under my username eHelen. Alright, let's get started and learn some more about the JDK and the JVM. So the Java Development Kit, or JDK for short, consists of many parts. First of all, we have the specifications, which in great detail describes what the Java language is, how the Java virtual machine works, and what constitutes the Java platform. Then we have the tools themselves that you all use for developing Java programs. For example, JavaC, the compiler from Java source code to class files. JShell, the REPL you can use to quickly evaluate small snippets of Java code. And also packaging tools like jar and JLink. And finally, we have the Java runtime environment, primarily consisting of the Java Virtual Machine, or JVM for short, and the Java class library. When there is a major release of Java, such as JDK 10, there are updates to many of these parts. For example, in JDK 10, the Java language specification was updated, and the most notable feature was the introduction of the local variable type invariance that you probably have heard about. The Java platform was also updated. For example, we have the new unmodifiable collections in JDK 10. The tools themselves are also updated. For example, in JDK 10, JavaC will provide nicer error messages, and JShell will start up faster. But for this talk, we're going to focus on the updates to the JVM in JDK 10. So, the Java Virtual Machine, or the JVM. The primary purpose of the Java Virtual Machine is to execute Java programs. Now, as you can imagine, that is a rather vast and complex task, so we're going to look at a concrete example here and see what it can look like in practice. You have written your application in Java, compiled it using JavaC, into class file, and perhaps package it up using jar into jar files. Your program probably make use of a bunch of libraries. These are most often found in jar files, for example on Maven Central. What is common for both your application and the library you use is that they will all make use of classes found inside the Java class library. Here you find classes such as string, ArrayList, hashmap, etc. Since Java 9, the Java class library has been modularized and is now found in JMod files inside the JDK distribution. What is common for all of this is that they are executed by the Java Virtual Machine. There are three major components to the Java Virtual Machine that make all this work: the GC, the runtime, and the compiler. And in this talk, it is these components that we're going to focus on. So the GC, which is short for garbage collector, is responsible for allocating memory and also reclaiming unused memory. So whenever you type new in Java, the GC is responsible for ensuring that there is memory for that object, and when the object is no longer in use, the GC is responsible for reclaiming it. The runtime is responsible for many parts, including loading and linking classes, interacting with the operating system to create threads and sockets and more, and also providing logging, diagnostic, and serviceability tools. The compiler is responsible for compiling your Java bytecode into highly effective machine code that runs as fast as possible. And the great news is that all of these components have received nice enhancements in JDK 10. So let's get started and start by looking a bit more into the new features for the garbage collector in JDK 10. So as I mentioned, the garbage collector is responsible for allocating memory. On this slide, I have created a small class person that has a private field called name and a constructor which allows you to set this name. And a little bit further down in this slide, I create a new person called John Doe. But what happens when the Java virtual machine will execute this instantiation of a new object of class person? Well, the JVM will allocate memory, and it could look something like the following. We get some memory for the person object. You can see the field name there with a pointer to a string object. The string object has in turn a pointer to the actual character array for the characters making up the string. And if we look at the character array, we see the length field is 8 there, and we also see the individual characters making up the string. This memory area, where the GC allocates memory, is commonly referred to as the heap. This heap is often very large. When you run your Java programs, it is typical to see heaps ranging from 1 to 256 gigabytes in size, but we have seen occurrences of multi-terabyte sized heaps. The heap contains billions of objects of different sizes and of different types. And the problem that the GC must solve is what happens when the heap is full. As we saw on the previous slide, the GC will keep on allocating and use more and more memory whenever you create new objects. But the heap, even though it's large, is finite, so something must happen when the heap is full. The typical algorithm used by most GCs and all found in the JVM is to first of all find the live objects. Not all the objects you were allocated are still in use, some are no longer being used. On this slide, the orange parts are the live objects, and as you can see, there are only parts of the heap that are currently in use. The next step, which is another typical GC algorithm, is to compact live objects towards one end of the heap. As you can see here in the example, we have now freed up space at the other end of the heap that can be reused for allocating new objects. The challenge here is that compaction can take a very long time, particularly when the heap is large or the heap contains billions of live objects. To make matters even worse, a Java application is often stopped during compaction, which means that your Java application can be stopped for many seconds. As you can imagine, this is not good for interactive programs such as servers or GUI programs. Let's say that you have written a network service that serves up HTTP requests, so when a user loads your website, you don't want your server to be stopped for several seconds, because that means that the user will have to wait for several seconds before being able to view your website. Similarly, if you're writing a GUI program, you don't want your game, for example, to freeze just because the garbage collector has decided to compact the objects. So, in order to tackle this problem, we made the G1 GC the new default memory management algorithm in JDK 9. Now, G1 isn't all that new. It was actually introduced way back in 6U14 and has seen support since 7U4. The goal of G1 is to provide both high throughput and low latency, and G1 tries to achieve this by utilizing a pause goal. By default, this pause goal is 200 milliseconds, which means that G1 will work hard to ensure that the application is not stopped for more than 200 milliseconds at a time. This pause goal is tunable, meaning you can set a higher pause goal, which most likely will result in more throughput, but also higher latencies. If you provide a lower pause goal, you will probably see less throughput, but you will also get a lower latency. Now, having a higher pause goal might be suitable for more throughput-oriented applications such as scientific calculations, whereas a lower pause goal might be better for more interactive applications such as servers or GUI programs. So how does G1 achieve this? G1 divides the heap into multiple regions. It is a so-called region-based garbage collector. Furthermore, when G1 finds all the live objects on the heap, it does so concurrently. That means that the Java application is not stopped while G1 finds all the live objects. It runs alongside the application at the same time. So G1 will keep on finding live objects, and furthermore, G1 will also keep track of pointers between the different regions. These three properties, dividing the heap into multiple regions, find all the live objects concurrently, and keeping track of pointers between regions, enables G1 to only having to collect a few regions at a time. That means that there are fewer objects to collect, which leads to shorter pauses, and there is also more information before a collection occurs, so G1 has more control over the pauses themselves. Now, if you were looking hard at the previous slides, you might have wondered, well, if G1 finds all live objects concurrently with my application, what happens if the heap becomes full before G1 has found all the live objects? That is a problematic scenario for G1 and one we work hard to ensure it's not getting into. But if that happens, then G1 will fall back to a secondary algorithm called a full collection. To make matters even worse, the full collection used to be single-threaded, which means that a full collection can take a very long time on large heaps. The great news is that this is finally solved in JDK 10. So JDK 10 introduces YEP 307 parallel full GC for G1. This means that the fallback algorithm that G1 only utilizes in the worst case scenario is now a parallel mark sweep compact algorithm. That means that this fallback full collection will now utilize all the CPU resources available if you have multiple cores. They will all be put to use to get out of this situation as quickly as possible. This significantly improves G1's worst case pause times. This is enabled by default in JDK 10. There is no need to set any flags or tune anything. It is delivered for you automatically and is available in JDK 10. The other nice enhancement to G1 in JDK 10 is the enhanced heap scanning. In order for G1 to be able to track the pointers between the different regions, it has to scan the heap quite a lot. This code is run very frequently from time to time, and for JDK 10 we took a long hard look at it and wrote it in the most optimal way we could think of. The result is that you will see shorter pause times for both young and mixed collections, and G1 will also use less concurrent CPU usage. This is also enabled by default. There are no flags that needs to be set to use this feature, and it's available in JDK 10. So let's have a look at the second component of the JVM, the runtime. As I mentioned in the beginning, the runtime is responsible for many parts: loading the Java classes, interacting with the operating system, providing concurrency primitives for your Java programs such as threads and monitors, providing logging and diagnostics and serviceability tools. But in this presentation, we're going to focus on two parts: the loading of Java classes and how the JVM and the runtime interacts with the operating system. So, Java classes. When you write your Java programs, you write them in source code in a .java file, and then you use javac to compile your source code into a class file, which is a binary file format. Later on, when you type Java to run your application, sooner or later there will be a call to the JNI function define class, which tells the JVM to load a class found in a class file and construct an in-memory representation of it that the JVM can use throughout its lifetime, so that, for example, the garbage collector and the compiler can have the information it requires about the objects on the heap. However, loading a Java class from a class file takes some time. First of all, the JVM must load the contents from the file itself. It must verify that the class file is correct, particularly that the bytecode is correct. Then it must create an in-memory representation for the JVM to use, which means it has to allocate a bunch of objects. And the runtime must also resolve and link references to other functions and symbols that this class uses. To make it even a bit more problematic, many times you restart the same Java program. You haven't changed anything, you just restart your program. For example, if you're in the cloud and you're spinning up new Java programs on demand. This means that all this work of loading all these classes, verifying them, resolving symbols and linking must be repeated every time the JVM starts, even though you did not change anything in your program. Can this maybe be optimized? Yes, it can. So way back in JDK 1.5, we shipped a feature called Class Data Sharing, or CDS for short. CDS stores already loaded and verified classes to a so-called shared archive file. This shared archive file is laid out in such a way that it can be quickly loaded by the JVM at startup. Also, if you're running the same program using many processes, this shared archive file can be mapped into all of these processes and thereby saving some memory. However, there were some severe limitations to the CDS feature shipped in JDK 1.5. It only worked with the client JVM, it only worked with the serial garbage collector, and it only worked with so-called system classes. So in JDK 9, we shipped enhanced class data sharing. So CDS now worked with the G1 collector, the parallel garbage collector, and the serial garbage collector. In JDK 9, CDS works with both the client and server JVMs, and it also even worked with share strings, but this is only applicable to the G1 GC. There was still one drawback here, and that is it was still only applicable to system classes. So in JDK 9, we also shipped application class data sharing, or AppCDS for short. This enables application classes to also be stored in the shared archive file. For example, if you recalled from the beginning of the presentation the little class called person, that class can now also be stored in the shared archive file and quickly be loaded by the JVM at startup. However, this was a commercial feature that was only available in Oracle JDK 9 if you use the flag -xx plus unlock commercial features. But in JDK 10, AppCDS was open sourced. If you have a look at JEP 310, Application Class Data Sharing, you will find more information about AppCDS and how to use it. But starting in JDK 10, it is now available in OpenJDK 10 builds that you can find on jdk.java.net/10. Using AppCDS results in even faster startup time compared to only using CDS, because there are now many more classes that can be stored in this shared archive file and quickly being loaded. And this is great if you're spinning up new JVMs on demand quickly. So how do you use AppCDS? First of all, you have to find out the classes that you want to share. A typical Java application might ship a lot of classes, but maybe not use all of them. If you were to put all of these classes into the shared archive file, that file itself can become very large, and you will also waste some memory while you recreate the classes upon startup when loading classes from that big shared archive file. So first step is to figure out which classes are actually used by the application and store those into a file. So you will run Java and you will set the X share flag to off. So since we're now creating our class list, we don't want any CDS to interfere, so we turn off all sharing and all CDS. Then we enable AppCDS by the flag -xx plus use AppCDS. We use the flag dump below the class list to tell the JVM to store the classes that has been loaded into this file. In this example, we name it app.lst. And then we run our application as usual, maybe putting some jar files on the class path or enabling some modules. And we provide the class with the main function. Now, for the second step, we now have app.lst, the file with the classes that has been used by application and loaded, which means that we are now ready to create the shared archive file. Now in step 2, we will once again run Java, but this time we set the X-share flag to dump, because we will now create the shared archive file. We again enable appcds with -xx plus use appcds. We tell the JVM about this class list file that contains the names of the classes that we want to share, which is found in app.lst from step 1. We also give the JVM the name for the shared archive file with the flag -xx shared archive file, and in this example I named the file app.jsa. And then we set up the class path or module path accordingly. Note here that I don't provide the name of the class that contains the main function, because in step 2 the JVM will only load the classes and then dump them out. It will not run your program. It will just load the classes from the class list in order to be able to create the shared archive file. Now in step 3 we are ready to make use of our newly created shared archive file by running Java, and we set xshare to auto. We'll come back to this a bit later, why auto and not on. We then enable appcds with the flag -xx use appcds and tell the JVM about the shared archive file we just created in step 2, namely app.jsa, and then we run our application as usual. Now the JVM will use the shared archive file and quickly load the classes upon startup. We use auto because sometimes the operating system might contain security features like address space layout randomization, and appcds relies on the feature of being able to put this shared archive file into a specific memory location. If you run with xshare on, the JVM will exit if it can't map the shared archive file into this memory location, which can be a bit troublesome if the OS is using ASLR. So if you run with xshare auto, you tell the JVM, please try to use the shared archive file that I created and provided to you, but if it's not possible, due to example of not being able to map the shared archive file into a precise memory location, just continue and load classes as usual. Alright, the second part of the runtime that has been updated for JDK 10 that I want to tell you about is how the JVM interacts with the operating system. So the runtime uses the operating system for many things, including creating threads, performing memory allocation, and also setting up sockets for programs that want to use them. It is important for the JVM to use the right APIs when interacting with the operating system, particularly in a world now full of containers. That means that we must respect the container boundaries and use the correct CPU APIs from the OS. In particular, it is not so good if the JVM queries the CPU directly to find out, for example, how many cores it has in order to determine how many threads it should use, because even though it can do so, the CPU might be shared among many different containers, and the JVM needs to respect those boundaries. This means that the JVM must be aware of Linux namespaces. What's great is that in JDK 10, the JVM now uses the correct interfaces. In particular, it uses the cgroups interface to find the memory limit, which means that the default heap size will no longer be way too big when you run the JVM inside a Docker container. It also uses the CPU set API to limit the number of cores available to the JVM, and in practice, this means that the default number of GC and compiler threads will now be correct. And finally, it also uses the PID namespace for the JVM's own attach API. This means that tools such as JMap can now connect to a JVM running inside a Docker container. Furthermore, in JDK 10, we have also set up a bunch of new flags, which provides a more intuitive way to set the heap size. In JDK 10, you find the flags mean ROM percentage, initial ROM percentage, and max ROM percentage. And all these flags allow you to set parts of the heap size to a percentage of the available ROM. This works great in combination with containers because there's no need to update these JVM flags when you are changing the container memory limits. If you decide to increase or decrease how much memory should be available to a particular container with a JVM running inside of it, the flags will still use the correct percentage of available ROM for setting up the heap. Taken all together, this means that JDK 10 now has a much better container story. Using app.js, you get faster startup, which is great if you're spinning up new JVMs on demand to incoming requests. The JVM also uses the correct operating system interfaces, which enables better defaults, for example for the number of threads and the heap size, and you get better tooling so that you can use JMap with your containers. And finally, you also get new flags for more intuitive heap sizing. So if you are running Java inside of Docker containers, make sure to upgrade to JDK 10. Alright, we're now going to have a look at the last component of the JVM for this talk, the compiler. So the compiler is responsible for turning the Java bytecode into very effective machine code that runs as fast as possible. But the road from bytecode to this effective machine code is rather long. So when you compile your source codes with javac to class files, these class files will contain bytecode describing how your Java program should be executed. When the JVM starts, it loads the class files and the bytecode inside them, and then it will start to interpret this bytecode. The interpreter looks at each bytecode in turn and then perform the suitable action. However, this is a rather slow way of executing bytecode, so if the interpreter finds out that a function is used a lot, it will use a so-called just-in-time compiler to compile that bytecode into more effective machine code. To start out with, it will use the C1, the first of the JIT compilers found in the JVM, to compile that bytecode. C1 is a good compiler that is fairly fast and produces reasonable machine code. It doesn't produce the best possible machine code, but it does produce that machine code fairly quick, which is good if your function is used a lot, but not a whole lot. So if C1 and the interpreter find out that a particular function is very, very hot, meaning it is used very, very frequently, it will use C2, the second JIT compiler in the JVM, to produce very optimized machine code. C2 is a very good compiler that is a little bit slower, but in turn generates very good and fast machine code. So you only want to use C2 for functions that are used very, very often. This setup gives a really good sort of bang for the buck scenario when compiling your bytecode. There's no need to spend a lot of CPU resources on using C2 to compile bytecode for functions that are very rarely, maybe even used once. Then the interpreter is more than fast enough. However, in JDK 9, there was an additional compiler introduced that works a little bit differently compared to the just-in-time compilers. JDK 9 introduced the ahead-of-time compiler called JAUTC. Now, JAUTC works similar to javac prior to your application being run with Java. So you are all used to running javac to compile your Java source code into Java class files. With JAUTC, you can now compile those Java class files into a shared library containing fairly optimized machine code. And then, when you run your application, you can tell the JVM to load the machine code found in the shared library and start to use that instead of using the interpreter. If it turns out that there's more optimization opportunities for the machine code found in the shared library, we can then utilize C1 and C2 to make further optimizations. Now, why would you want to do this? Well, as we saw on the previous slide, the road from bytecode to highly optimized machine code can be a little bit long for your particular application. For example, getting through the interpreter, warming everything up means that letting the JVM find out which functions are hot and which are not can take a little bit of a time. Using JUTC and providing this shared library means that your code will run faster from the get-go and can still be optimized if needed. However, there were some limitations to the JAUTC compiler found in JDK 9. It did not support all bytecodes, it only worked on Linux, and there was only experimental support. JDK 10 now features an enhanced AUT compiler So the AOT compiler JAOTC in JDK 10 now supports the invoked dynamic bytecode, and it works equally well on Linux, macOS, and Windows. But recall, there is still only experimental support for the JAOTC compiler. If you want to use it, run JAOTC --output, set a name for the shared archive file, libapp.so in this case, and then provide your class files as input. The other new feature in JDK 10 for the compiler component is that a new JIT compiler is introduced, namely Graal. So in JDK 10, you can choose to have a compilation set up utilizing the interpreter C1 and then replacing C2 with another JIT called Graal. So Graal only has support on Linux for now and is only experimental support, which means that Graal may or may not make your application go faster compared to using C2. But if you want to try out Graal, you can do so by running java-xx unlock experimental VM options -xx use JVM CI compiler. Now, those were the updates, the major ones, to the JVM components in JDK 10. Now let's peek a little bit into the future and see what's next. So JDK 11 is already scheduled for release in September 2018, and here we see the new release cadence really kicking in. Even though we're only a few months away from JDK 11, there are still some real nice features that has gone into JDK 11. We find the dynamic class file constants as described by JEP 309. There is also the local variable syntax for lambda parameters as described by JEP 323. And for the JVM in JDK 11, there are already great improvements to the various components. For the GC, we now have concurrent rebuild of remember sets for G1, and this is a very great feature that will decrease memory usage, decrease CPU usage, and make G1 overall more effective. For the runtime, there has been improved metaspace allocation that probably and hopefully will result in some memory savings, and the compiler team now builds Graal on both Windows and Mac. Now, if you want to try out JDK 11, this is the right time. Because if you want to try it out, find out that something doesn't really work the way you think it should, or you maybe have come up with a better way, now we need your feedback. If we get the feedback maybe 1 or 2 weeks prior to release, there won't be enough time to act on it. So please go ahead and download the early access builds for JDK 11 from jdk.java.net/11. You might be wondering, even though JDK 10 just was released and JDK 11 is due in a few months, how can there be time to get new features into 11? The truth is that there are many projects spanning multiple releases that takes a bit time to develop and bake and get ready, and I want to share some updates on a few of them with you today. So there are a lot of great work going on in the OpenJDK community. We see exciting projects such as ZJC, Portola, Valhalla, Loom, and Panama. These are only a few examples of the many projects that are currently being developed, and if you want to get more information about these projects, head to openjdk.java.net for more information. In this talk, I want to just quickly show you some introduction to 2 really cool projects, ZJC and Project Portola. So as a GC developer, I'm very happy to tell you about ZJC, which is a new, scalable, low-latency garbage collector for the JVM. ZJC provides pause times that are below 10 milliseconds. They are always below 10 milliseconds. These pause times do not increase with heap size, nor do they increase with live set size. And ZJC is built to work well on heaps ranging from a few gigabytes to multiple terabytes in size. Now, the key to achieving these low pause times below 10 milliseconds, even though the heap might be terabyte in size, is to do a lot of work concurrently. ZJC will find all live objects concurrently. It will compact these live objects concurrently So the objects will be compacted as your Java program is running. We will not stop the JVM for compaction. And finally, it even processes references concurrently. If you want to try out ZGC, there are already early access builds available, so please head to jdk.java.net/zgc to download the build and try it out and see how it performs on your application. If you want to know more about ZGC, you can find more information on the OpenJDK main wiki page for ZGC. The other project I want to show you is Project Portola. Project Portola is a port of OpenJDK to Alpine Linux. Alpine Linux is a small, secure, and lightweight Linux distribution that uses the Muscle C standard library. You may not have heard about Alpine Linux, but the cool property of Alpine is when you use it as a Docker base image. The total size of the Alpine Linux Docker base image is only 4 MB, and this is really tiny. You can compare this to Ubuntu when used as a Docker base image weighs in at a whole 120 MB. Now JDK 9 introduced a tool called JLink, which enables you to create your own small Java runtime environment consisting of precisely those modules needed for your Java application. If you combine these small Java runtime environments tailored for particularly your Java applications together with the Alpine Linux Docker base image, you wind up with very small Docker images for your Java apps. For example, if you use compression and many of the features found in JLink, the Docker image for just java.base using Alpine as the base image is only 40 MB. Now, your application probably requires a bit more than just the java.base module, but this example shows that you can get very small Docker images using this port. If you want to try out Project Portola, there are early access builds available at jdk.java.net/11. So this would be JDK 11 builds ported to Alpine Linux. If you go to the download page, look for the Alpine Linux download option. And if you want to know more about Portola, head to openjdk.java.net/project/Portola. Now, that was all for today, so let's quickly summarize and recap what we've seen today. So JDK 10 contains some great improvements to the JVM. You get the G1 parallel full collections, you get apps.jds in the OpenJDK builds, better container support, and improved AOT, and a first glimpse of the experimental Graal support. But this is not all. There are more than 400 enhancements going into the JVM in JDK 10, including faster startup in general, which I know a lot of you care about. There are more than 500 bug fixes to the JVM in JDK 10, and it is not like the JVM is totally broken before JDK 10. Many of these bug fixes include test fixes, refactorings, etc. And there has been more than 100 people contributing to the JVM in JDK 10 from many different companies. So please download, try out, and enjoy JDK 10. Head to jdk.java.net/10 to get your download. And if you're on Twitter, make sure to follow @OpenJDK and @Java to get the latest news. Thank you.